Good morning, good afternoon, and good evening to those in Europe that are joining. Thank you for joining day 5 of our 2020 virtual user meeting, Voltage-Gated Ion Channels, Fenestrations as a Drug Access Pathway. My name is Jason Villagomez, Marketing Manager at Nanion Technologies, and will be your moderator for today's presentation. By default, all participants are muted, and upon completion of the presentation, I will open the floor to questions. We encourage you to submit questions throughout the course of the presentation. It is now my pleasure to introduce Professor Tamer M. Gamal Eldin, University of Washington, Seattle, presenting Voltage-Gated Ion Channels, Fenestrations as a Drug Access Pathway. I will now hand over to Tamer for the start of the talk.
Hello, everybody. Can you hear me?
Yes, loud and clear.
Okay, great. So, good morning, everybody on the West Coast of the United States, if you are here, and good evening, everybody in Europe or other areas where it's night already. So, it's my pleasure actually to participate in Nanion and Friends talks. And today I'm going to talk about fenestrations as a drug access pathway. So I'd like to start by I should say actually I'll focus in my talk on voltage-gated sodium channels. However, I will actually, by the end of the talk, I'll mention other voltage-gated ion channels, but my focus will be on voltage-gated sodium channels. So as you all know, voltage-gated sodium channels are integral membrane proteins that change conformation in response to depolarization of the membrane potential, and it opens its gates and conducts sodium ions from the outside of the cell to the inside, down the concentration gradient of sodium ions, and that actually trigger the action potential and propagate the action potential. So sodium channels are very important actually to nerve conduction in many organs in the body, skeletal, cardiac muscles. It's important for secretion of many hormones. It's important for neurotransmission and many other processes. So let me mention first the topology of voltage-gated sodium channels. So voltage-gated, eukaryotic voltage-gated sodium channel is composed of 4 homologous but not identical domains. Each domain is composed of 6 segments. The first 4, the green segments here, S1 to S4, form the voltage sensing domain. And specifically S4, which is rich in basic residues, form the main actually voltage sensor. On the other hand, segments S5 and S6 from each domain come together and form the conduction or the pore which conducts the ions. So this is the alpha subunit, what we call the alpha subunit of a eukaryotic voltage-gated sodium channel. In addition, we have additional beta subunits, which comes in different flavors and bind to voltage-gated sodium channels. So some have 2, some have 1, and so on. And they are important for the expression and the tuning the kinetics of voltage-gated sodium channels. So to date, we have actually, 9 different isoforms if we don't include the NAV-X. So we have well-known 9 different isoforms of eukaryotic voltage-gated sodium channels, NAV 1.1 up to NAV 1.9. NAV 1.1, 1.2, 1.3, and 1.6 are mainly expressed in the central nervous system, while 7, 8, and 9 are mainly in the peripheral nervous system and are known as the pain sodium channels, specifically 1.7, where on the other hand, we have the NAV 1.4, the main skeletal sodium channel, 1.5, the main cardiac sodium channel, and yeah, so these are the 9 different isoforms. On the other hand, we learned a lot from different prokaryotic voltage-gated sodium channels. But the topology of these channels are very different, actually, it's very different. So it's a homotetramer, meaning that they have 4 identical subunits that come together and form a functional channel. Despite the differences in topology between eukaryotic on top and prokaryotic on the bottom, the 3D structure of both of them, so the cryo-EM structure of 1.4 on top, the crystal structure of NAV-AB on bottom, they are pretty similar. So that tells you how conserved the voltage-gated sodium channel is since the beginning of life. There are minor changes. So in prokaryotic sodium channel, the C-terminal is known to be long, as you can see here in a side view of NAV-AB structure, which doesn't exist like this in most of the eukaryotic sodium channels. So let me remind you that voltage-gated sodium channels is actually an electromechanical coupling device, meaning that when the voltage sensor, which shown here, so I'm showing just one domain out of the 4 domains of the voltage-gated sodium channel, when the voltage sensor senses any change in the electric field across the plasma membrane, it starts actually to move. And this movement is transduced to the Pore domain here via the electromechanical coupling device, which is the S4-S5 linker. So as you can see here, this movement of the S4 mainly kind of pushing the S4-S5 linker, and that leads to opening of the channel. If you have a top view, you can see that this movement of the voltage sensor leads to a dilation of the activation gate of the pore, which would allow actually the hydrated sodium ions to pass at a diffusion rate actually through the pore. Since it's voltage-gated sodium channel, there is actually a voltage threshold, meaning that if this changes in the voltage across the plasma membrane happened within the range of -100 to -50, most of the time that will not lead to an ionic current. So it will not lead to the opening of the channel. Only when these changes, these electric changes hit the voltage threshold, which is around -50 plus minus, of course, it's different from one isoform to another one, the channel gates open and sodium ions will rush into the cell until an equilibrium between the electric potential and the concentration potential, or the concentration gradient, happens at the reversal potential here. And that depends very much on the concentration of sodium ions intracellularly and extracellularly. So because you can actually think about sodium channels, voltage-gated sodium channels, as the triggering molecular machine for electricity in our body, any missense mutation can lead to severe diseases. And up to date, more than 1,000 diseases, or actually disease-related mutations, have been attributed to voltage-gated sodium channels. Half of these disease-related mutations exist in either the neuronal sodium channel NAV 1.1, leading to many diseases like epilepsy, autism, and many others, or in the cardiac sodium channel NAV 1.5, which leading to diseases like arrhythmia and cardiomyopathy, and many other diseases. Today, I'm going to, take arrhythmia as an example to explain how fenestrations are very important to deliver actually, or as an access pathway for antiarrhythmic drugs. So let's define arrhythmia. It's the improper beating of the heart. So meaning that the heart can beat too fast or too slow or have an irregular rhythm, which is called, if it beats too hard, too fast, it will be tachycardia, as you know. When it beats too slow, it will be, or actually it's known as bradycardia. The electrical communication in the heart happens through network of voltage-gated sodium channels, potassium channel, calcium channel, HCN channels, many other channels. So any disruption in the communication between these ion channels may lead to arrhythmia. So people who suffer from arrhythmia, they feel kind of fluttering in the chest pain, fainting, dizziness. And the treatment actually starts with antiarrhythmic drugs. And sometimes the patients have to introduce implantable devices to adjust their heart beating. And eventually, if it doesn't work, they have to go through surgery. So the cardiac action potential, as I mentioned, is actually an interplay between different ion channels, voltage-gated ion channels, beginning with the sodium ion channel, which trigger the action potential and is responsible for this upward phase of the cardiac action potential. Once it opens, voltage-gated potassium channels start to kick in and try to repolarize the membrane, but at the same time, voltage-gated calcium channel, and specifically CAV 1.2, opens and keeps the membrane depolarized for a few hundred milliseconds, which make the cardiac action potential strong enough to help the heart to beat and pump the blood to the whole body. And then again, potassium, voltage-gated potassium channels and inward rectifier potassium channels start to activate and repolarize the membrane, bringing it back to the resting potential. So if any missense mutation happens in one of these ion channels, it will lead to arrhythmia. And for that, over the last few decades, many drugs have been developed to cure arrhythmia, actually cure the symptoms, not the disease itself. So if arrhythmia is caused by a missense mutation in voltage-gated sodium channel 1.5, class 1 antiarrhythmic drugs like quinidine, lidocaine, flecainide, propafenone, and others are used to treat arrhythmia symptoms. If it's caused by a missense mutation or malfunction of potassium channel, class 2 will kick in to be the potential therapy. Likewise, class 3. And if the missense mutation occurs in voltage-gated calcium channel like 1.2, class 4 calcium channel blockers like verapamil and diltiazem will be the main strategy for the therapy of the arrhythmia. So today I'm going to focus on voltage-gated sodium channels and specifically on 3 drugs, flecainide, lidocaine, and benzocaine. So I like this resemblance of voltage-gated sodium channel to automatic door. So if you think about the automatic door, you approach the door and there is a sensor on the top that senses you, either the IR, infrared, or your mechanical movement, whatever. You have a sensor which senses the existence of somebody in front of the door. And then this sensor transduces the stimulus into the door to open the door. In voltage-gated sodium channel, we have four sensors actually instead of one. So shown here in the circles, the green part here of the channel, this is the top view of NAV-AB, like the sensor that the door has. And both of them, the automatic door and the voltage-gated sodium channel, they have a gate in the middle. And both of them have an electromechanical coupling device which transduce the stimulus into an action to open the door, likewise here in voltage-gated sodium channel. So when arrhythmia occurs, you know, something like what you see here in the picture happens. So the door, the activation gate of the sodium channel open and closes irregularly, you know, either too fast, too slow, or in an irregular rhythm. So if you are responsible for this door and they asked you to stop the door from, you know, from this irregular movement, and if you know a little bit about the mechanics of the door, maybe you will choose to disable the sensor up there. Or you may decide actually to disable the connection, the yellow wire here between the sensor and the door. But if you don't know anything about the mechanicals or the electronics of the door, simply you can bring a physical thing and put it against the two sides of the door just to stop the door from this irregular rhythm and in order not to hurt anybody. Interestingly enough, that 99% of antiarrhythmic drugs working actually by the third mechanism, blocking the gate. So all the drugs that we use nowadays as antiarrhythmic drugs, blocking the pore of the voltage-gated sodium channels. And as you can see, the pore is kind of not accessible actually. The drug has to reach its binding site inside the pore by passing through the outside protein architecture. And here comes actually the importance of the fenestrations of sodium channels in general and 1.5 in particular as an access pathway for antiarrhythmic drugs. Long time ago, Bertil Helle suggested that there are two pathways for antiarrhythmic drugs to reach its receptor site. So when the activation gate is open, the drug, especially the charged part of the drug, can enter the binding site via the activation gate this way. But if the inactivation gate is working, so meaning that the channel is in the inactivated state, or if the channel at the resting state, there is no way that the drug can go and reach its binding site through the activation gate. And the only plausible pathway would be through the membrane phase, this hydrophobic phase. From 1977 up to 2011, and despite we have an humble evidence from electrophysiology data, however, nobody actually were able to see the fenestrations or any connection between the internal part of the channel, which we call the central cavity, and the outside or the membrane phase of the channel, of the plasma membrane. So it wasn't until 2011 when our lab managed to crystallize the first ever voltage-gated sodium channel, NAV-AB, and showing for the first time that there is a connection between the central cavity, the internal part of the sodium channel, and the lipid phase, And we found that there is one specific residue that shaped the entrance of the fenestrations, which is the phenylalanine 203 by NAV-AB numbering. If you have a top view of NAV-AB with a cut through the pore domain, you will see the 4 fenestration as 4 tunnels connecting the outside of the channel, the membrane phase, to the internal part of the channel where the binding sites of antiarrhythmic drugs and the local anesthetics exist. So these green and blue parts here is where actually the antiarrhythmic drugs bind. So this is short movie showing the 4 fenestrations of NAV-AB. So the green parts are the voltage sensing domains, and the blue one is the pore domain. And you can see here the hole here. You can see the other side from here. So these are the fenestrations here, which connect the lipid phase to the internal side. And the red part here is the binding site of Flecainide. So voltage-gated ion channel, voltage-gated sodium channel has 3 different states. Actually, they have more than 3 states, but 3 main states, if you will. When the membrane is hyperpolarized, we have the resting state where the activation gate, so I'm showing it here as just the pore domain, a cartoon of the pore domain showing the activation gate, the fenestrations, and the selectivity filter. So at the resting state, the activation gate is closed. The inactivation motif is out of the cell, and apparently the fenestrations are open. If you depolarize the membrane, the channel will open and sodium ions will rush into the cell for a short time. And apparently also the fenestration are still open, maybe different conformation, but still open. And in the inactivated state, when the IFM motif move and block the channel from the inside, and the selectivity filter will follow if the channel enters the slow inactivated state and collapse. And the only accessible pathway to the internal part of the channel would be through the fenestrations. So from EFES data, we know that, or actually let me mention first that, or actually stress on the point that the antiarrhythmic drug binding site is kind of hidden. So unlike any other receptor, membrane receptors, where the binding pocket of the ligand is exposed to the external or internal part of the cell, the binding site of antiarrhythmic drugs is kind of hidden inside the sodium channels. So it's not enough, or actually it's not reasonable to talk only about the affinity of the binding site if the accessibility to the binding site is not available. And by accessibility, I mean to say that there are 2 gates which controls the entrance of the antiarrhythmic drugs and other drugs to the central cavity. The activation gate on one hand, and the fenestrations on the other hand. So EFES data showed that there are 3 modes of antiarrhythmic drugs interaction with voltage-gated sodium channels. So at the resting state, where there is no accessibility except through the fenestration, we can measure what is known as resting state potential. So you wash in your drug, and you measure the first pulse after washing the drug and compare it to the control measurement, and you can see a reduction in the peak current, and this is what we call the resting state block. And usually it's, in most of the channels, it's it has low affinity, if you will. So there isn't that much channels that are blocked during the resting state. So like on average 10 to 10%, 10 to 20%, sorry. If the channel open by depolarizing the membrane, the drug have a bigger chance, especially the protonated or the charged part of the drug, to enter the channel through the activation gate. And if you keep pulsing at a reasonable rate, you will see a phenomenon called use-dependent block, meaning that the drug binds to the central cavity, to its binding site, and it's unable to dissociate during the resting or during the short hyperpolarizing pulse to the negative potential. And interestingly enough, the state which have actually the most affinity or the highest affinity is in most of the, in case of most of the antiarrhythmic drugs and local anesthetics, is the inactivated state. And despite the channel actually is blocked from the inside and from the outside, so the selectivity filter is apparently collapsed, and anyway, the size is not big enough to allow drugs like Flecainide and other antiarrhythmic drugs, and the internal part is blocked, and the only accessible pathway is through the fenestration. This actually state shows the highest affinity to most of antiarrhythmic drugs. So that, I think, shows the one aspect of the importance of studying the fenestration as an access pathway to drug entry. So there is one residue which is known to be responsible for this phenomenon, use-dependent block, which is the phenylalanine in segment 6 of domain 4. So it has been shown that if you mutate this phenylalanine to alanine, you can abolish actually the use-dependent block. So on the left side here is the wild type, showing after 20 pulses, you can block most of the sodium current by use-dependent block with 200 micromolar of lidocaine. If you have the same concentration applied to this mutation, F1764A, you will get only the resting state block, but you will not see any use-dependent block. So does it mean that we have two different affinities belonging to two different binding sites, or it's two different affinities for the same binding site? So this issue has been in debate for more than 40 years now, and the first hypothesis came from Bertel-Hille, which is modulated receptor hypothesis, where he suggested that actually there are two affinities for the same binding receptor. So at the resting state where the drug decides to go through the hydrophobic pathway, the drug takes a pause that will not allow it to interact with the phenylalanine. So the affinity will be low. But at the open state and with the conformational changes that follow the opening of the channel, the drug actually interacts with the phenylalanine, probably with the cation pi interaction with the benzene ring of phenylalanine, and produces actually the high affinity interaction of the drug. Another hypothesis, which is less famous actually compared to the modulated receptor hypothesis, which is the guarded receptor one. So the guarded receptors say that, or actually argue that there is one constant affinity, but it's all a game of accessibility. So at the resting state where the internal site, the binding site of the channel is not very much accessible because the fenestrations are not wide enough in most of the eukaryotic channels to allow the passage of antiarrhythmic drugs, so the apparent affinity is low. But in the open state where the two gates are open and much more drug can reach its binding site the affinity goes higher. So we decided actually to tackle this problem, taking the advantage that we are able to crystallize NAV-AB, and that was before the, resolving the cryo-M structure of many eukaryotic sodium channels. So we said, okay, let's study the fenestrations in NAV-AB and see how much it contributes to the antiarrhythmic drugs block. Interestingly enough, we noticed that NAV-AB showed actually significant, very significant actually resting state block. So if you hold NAV-AB at very negative potential and wash in 10 micromolar of Flecainide, and the first pulse after washing in the drug, you will see like almost 50% block of the channels. This is almost the affinity of eukaryotic sodium channels. And more than that, we found that the use-dependent block is very minimal in NAV-AB. So if you keep pulsing at 1 hertz or 10 hertz, you don't see that much additional block in case of NAV-AB. And we interpret this data that the phenylalanine that I mentioned earlier, which is responsible for the use-dependent block phenotype in eukaryotic sodium channel like 1.5, doesn't exist in NAV-AB. Instead, we have a threonine in its place. And because it has no ring, so the cation-pi interaction, that is the potential mechanism of interaction of antiarrhythmic drugs with phenylalanine, it doesn't exist here with threonine, so there is no use-dependent block. So we continued actually and decided to co-crystallize NAV-AB with Flecainide. And we found that Flecainide actually bind in the central cavity, interacting with threonine 2,6, which is the equivalent of phenylalanine. And the amino part actually is facing the this selectivity filter here. So you can imagine a repulsion in addition to maybe physical interaction with the sodium ions and blocking the sodium ions. To confirm that this is really the binding site of Flecainide, we mutate threonine 2,6 to alanine, and we found a drastic actually reduction in affinity, around 17-fold reduction in affinity from 7.2 micromolar in case of wild-type NAV-AB to 133 micromolar in case of T2A mutation. We did the same with Lidocaine, and we found that it binds to the same binding spot. And again, the T2A mutation reduces the affinity of Lidocaine binding by around 18-fold, from 135 micromolar in case of control to 2.4 millimolar in case of T2A mutation. So, as I said, we were wondering about the role played by the fenestrations. And since we have 4 identical fenestrations, because NAV-AB is a homotetramer voltage-gated sodium channel, we found that the mean actually residue which shape the entrance or the narrowest part of the entrance of the fenestration is the phenylalanine 203. So we decided to mutate it either to tryptophan, bigger residue, which we hypothesized that it will block almost completely the fenestrations, and in another case to alanine, which potentially will increase the size of the fenestrations. So we started with Flecainide, and as I mentioned, the affinity of NAV-AB to wild-type NAV-AB to Flecainide is 7.2 micromolar. When we made the fenestrations much smaller by the F2W mutation, we found 6.5-fold rightward fold shift in the affinity of Flecainide. So the affinity became 6 micromolar instead of 7.2 micromolar. On the other hand, when we mutated the phenylalanine 203 to alanine, so making the fenestration much bigger, at least theoretically, it actually increases the affinity by 7-fold, and it became 0.9 micromolar. So we have a change by 50-fold in both directions by changing the size of the fenestration. And as I said, this is kind of the apparent affinity. We didn't play with the binding pocket itself, but we controlled the axis pathway to the binding site. Then we start to kind of rationale the effect of the volume or of the size of the drug compared to the size of the fenestration. So we said that if Flecainide, or actually if these mutations, F2W and F2A, causes this 7-fold on both sides change in the affinity or the apparent affinity of the drug, what would happen if we study the effect of these two mutations on another drug, much smaller drug, actually Lidocaine, which has a volume of 245 angstrom cubed and polar surface area of 32 angstrom squared. So the volume-wise, it's Lidocaine is like 2/3, a little bit more than 2/3 the size of Flecainide. You know, if you take the measurement via the surface area, it's around half, a little bit more than half. So you would expect, or actually I have to mention that we developed an empirical equation saying that the size of the new drug compared to Flecainide size multiplied by the shift causes by the mutation F2A or F2W. In case of Flecainide, so the 6.5-fold or 7-fold, multiplied by this change in the ratio of the size would give us the new, or the expected actually, shift in the IC50 of the mutant with the new drug. Meaning that we should expect 3.5 to 4.5-fold change in the affinity of lidocaine if you study its effect on F2E mutation or F2W mutation. So indeed, we found that F2W mutation showed 3.4-fold less affinity compared to the control. So you can see here the affinity became 458 micromolar compared to 135 micromolar in case of control. But interestingly enough, we found that the affinity of F2A is the same as the affinity of the wild type. We interpret this data that the size of the fenestrations of the wild type is wide enough for the diffusion of the lidocaine through the fenestrations. So any increase in the size does not lead to an increase actually in the apparent affinity. And to prove or disprove this hypothesis, we switched actually to a much, much smaller drug, which is benzocaine, which has a volume of 157 angstrom cubed. So it's like less than half the size of Flecainide. And we said that the F2A, F203A mutation should show the same affinity as the wild type. And indeed, we found that. So this means that lidocaine size is the kind of the borderline of the size of any antiarrhythmic drugs or local anesthetic drug. Any drug smaller than that will pass smoothly through the fenestrations of NAV-AB. Then we said, okay, so what about the F2W mutation? We still have a big difference. And if F2W mutation will put a constraint on the diffusion of benzocaine, we should expect a 3-fold shift in affinity compared to wild type. And indeed, we found 2.9-fold rightward shift in affinity of F2W compared to the control. Then we said, okay, let's go ahead and get the crystal structure of the F2A mutation and the F2W mutation to see if physically we can see change in the size of the fenestration or not. When we crystallize the F2A, we see huge fenestrations. So the fenestration increased dramatically from around 4 by 5 angstrom, roughly, depending on where you measure, to become 12 by 13 angstrom. In contrast to that, the F2W mutation actually narrows the fenestration dramatically, so it became less than 3 angstrom. So I mentioned earlier that fenestration is really constitute the access pathway at two states, the resting state and the activated inactivated state, specifically the inactivated state. And as we know that antiarrhythmic drugs target actually, the main point of antiarrhythmic drugs that it targets the channels that is going crazy. So it opens and closes in a irregular way. And that's why the affinity to the open and inactivated state is much higher. And this is the point, if the affinity of the malfunction channel is higher towards the drug, so we should actually study the two pathways, not only the activation pathway that most of the people think about, but the other pathway, which is the fenestrations. Why is that? Because at any point, actually, 30 to 60% of voltage-gated sodium channels are inactivated. So this is the normal voltage-gated sodium channel, not the malfunctioned. And in case of malfunctioned voltage-gated sodium channels, this percentage actually goes higher. And you have to think about that the only access pathway for the drug would be through the fenestrations. In addition, in ischemic patients, for example, the myocytes are actually at more depolarized potential, which actually put a big proportion of voltage-gated sodium channels 1.5 in the inactivated state. And again, the only pathway would be through the fenestrations. Another point is any drug, any of the antiarrhythmic drugs has a neutral form and a charged form. Lidocaine, for example, with pKa of 7.7, at neutral pH, 35% of lidocaine will be in its neutral form. And the neutral form, the only pathway that they can take is through the hydrophobic pathway. Likewise with flecainide and propafenone, where the neutral form would be like 1% in case of flecainide and 4% in case of propafenone at physiological pH. Another point that I found through the research with my research with fenestration is that many of the missense mutations which lead to arrhythmia, it changed the size of the fenestration dramatically. And now you can think about why flecainide in some patient causes proarrhythmia and actually enhance arrhythmia instead of blocking arrhythmia. I'm showing you here some of these mutations in NAV 1.5. All of these mutations either shape the fenestrations in some domains like 1, the fenestration between domain 1 and 2, 2 or 3, 3 or 4, 4 or 1, or at least close to the fenestration that if you make a change in it, it will eventually change the shape of the narrowest part of the fenestrations. So that tells us that you cannot actually treat every patient who has arrhythmia with the same drug. The genotyping of the patient is very important because one drug that will be effective with one patient will be drastic and fatal actually with another patient. So it turned out that fenestrations actually are conserved in most of voltage-gated ion channels. And here I'm showing you the 4 fenestrations of the cockroach voltage-gated sodium channel NAV pass, showing actually 4 different fenestration with different size. That's very interesting. So you can see the fenestrations between domain 3 and domain 4 is much bigger than the fenestration here, where fenestration of domain 1 and 1 and 2 and 4 and 1 almost closed. We have actually also noticed that many other channels like the eukaryotic NAV 1.5 have fenestration with different sizes, NAV 1.7, where fenestration is closed here in the resolved structure. And with calcium channel and potassium channel also, you can see the fenestrations. And in some of these structures, actually, it was clear that, all of these structures are resolved at 0 millivolt, where you would expect that the channel is already in the activated or inactivated, mainly inactivated state. So the activation gates are closed, and the only pathway for the drug, which you see here on the left, flecainide, on the right, diltiazem, will be actually through the fenestrations. So this is another proof that fenestrations fenestration plays a big role in delivering the drug to its binding site. So that actually, take us to the last point that I want to mention about fenestration, that it has a dynamic change in its shape. And this is one example here from actually from calcium channels showing different state of the calcium channels. And you can see the dynamicity of the fenestrations, that it changes size from one state to another state. So here it's very open. And now if it goes to another state, it will change the shape. So fenestration will be very important in designing some drugs that will act as an activator. So the fenestrations at the resting state have to be open enough to allow the activator to enter and do whatever it's going to do to push the equilibrium of the channel into the open state. So there are a lot to say about fenestrations, but I have to end here and just remind you about the main points that I mentioned in my talk, that fenestrations are a very important access pathway for antiarrhythmic drugs and local anesthetics. And as I mentioned in the last slide, it may also play a crucial role as an entry pathway for ion channel activators at the resting state. And as I mentioned earlier, the 30 to 60% of the voltage-gated sodium channels are inactivated at any time. At this state, the fenestrations are the only route for drugs like antiarrhythmic drugs. The fact that most of the drugs have different forms, neutral and charged, showed us that the neutral form will take the fenestration pathway, and that shed more light on the importance of fenestrations. In order to understand, the mutations which cause some diseases, you have to really study one single mutation and correlate it to the action of the antiarrhythmic drugs specifically, because some mutation cause a change in the biophysical properties of the channel, so it doesn't fit anymore the specific drug, because it changes either the size of the fenestrations or the availability of the channels. And this is just what I just mentioned. So I think eventually the tailored medicine would be the right approach to treat diseases which have the same phenotype like arrhythmia, but the genotype is very different from one patient to another one. So yeah, I would like to end by this, and thank you very much for your attention.
Thank you so much, Tamer, for getting us more detail into your work in fenestrations. I now open the floor up to some questions. So you're happy to type in the chat window, or if you'd like to keep them more personal and actually speak, that's also fine. One open question that I had while listening to all of this, you mentioned fenestrations and arrhythmias. Do you see this applicable to other diseases as well?
That's a good question. Actually, I mentioned that the drugs that we use right now bind to the central cavity of the channel, but in reality, most of the drugs actually, like hypertension drugs, bind also to the same area. So I see that also fenestrations that also a potential access pathway for other drugs like hypertension drugs.
Maybe you could go a little bit into the screening that you used in terms of the technology. That was something that I didn't quite catch on in terms of, you know, the amount of time that it took to analyze all of this data that you presented.
Yeah, all of these data actually were done by the classical reg, you know, so manual e-phase reg. But if you want to test the validity of this idea on a big, you know, you have to really test a lot of drugs with different sizes, different pKa, and, you know, really to get to the same conclusion that I mentioned, you know, that it's not applied only to the three drugs that I mentioned, Flecainide, Lidocaine, and Benzocaine, and that's neat really, you know, something like automated patch clamp, which we consider actually to you know, continue in this direction.
Okay, perfect. Then I think that's a good gateway for me to end, and I will transcribe the webinar. Naturally, if you want to rewatch the on-demand copy and address questions, I'll make sure to add Tamer's information in the description, as well as the team here at Nanion in terms of looking at the automated patch clamp systems. And yeah, I look forward to seeing more in this direction from you and your group, and hopeful that you can apply this into a larger screening pool, like you mentioned, with the automated capabilities. So we're very much looking forward to your continued research in this field.
Thank you.
Thank you so much. We wish everyone a good day, and thank you for your attendance throughout the course of the week.
Thank you.
Take care. Bye.
Bye.